In this section, we are going to talk about energy considerations in more detail. So throughout this course, in number of lessons, we referred and identified energy consumption as a significant important factor when we are designing IoT applications. When we are designing IoT systems, there are a number of key constraining factors that we need to consider. Energy power, bandwidth, latency, ongoing maintenance, environment, sustainability, and velocity, variety, veracity, and volume. Out of these all constraints, energy and power is one of the most important constraints that we need to handle, because that constraint also connected to all the other constraints that we mentioned as well. For example, ongoing maintenance and energy is pretty much connected, because if the choice that you make on the energy and power has a direct impact on whether someone need to go and change the battery or recharge the battery or develop some kind of mechanism to harvest energy. All IoT devices need some access to power sources. Even some of the components like RFID tags, which are powered by the signal that sent by a RFID reader, still needs to harvest the power from the signals in order to respond. Previously, we discussed that network communication is one of the biggest power consumption activity in IoT systems. So one of the ways that we can think about minimizing power usage is to adopt low power wide area network, which sometimes can have a long battery life exceeding 10 years. However, if you are using the low power to power the IoT devices, you might be looking at very small amount of payloads and very less frequent data communications. So it is always going to be a trade-off between how much data you need, how frequently you need, and how frequently you are willing to recharge or replace the batteries. This table summarizes differences between different energy sources. So we're starting from 1 milliampere hour kind of capacity to the 1 kiloampere capacity for large scale energy storage. As you can see on each of the columns, there are different requirements by different IoT products and solutions. Some of the products and services need higher capacity, higher reliability, longer lifetime. But the other ones need rechargeable energy harvesting, rapid discharge, long lifetime. Maybe they want to be implantable in bodies or deploy in remote places. You cannot replace the batteries frequently. So in this table, I just want to give you a snapshot of what are the different power sources and what kind of requirement each of these categories might have. It is also important to note that the network topology and the choice of the protocol both have an impact on the power budget. For example, in some scenarios, a point-to-point link created using a proprietary sub-gigahertz protocol may seem to be more appropriate because it requires a low demand on power from a battery. So that is why sometimes we see in smart home devices they use proprietary low energy protocols. However, because of the point-to-point nature, it limits the scope where and how the sensors can be deployed. In contrast, a star configuration built on either 2.4 GHz or sub-gigahertz technologies increase the flexibility that you can add multiple sensors and multiple different nodes together. But because of the increase of the complexity, it could also increase the radio frequency traffic, therefore increases the consumption of the power. The third option is mesh configurations, such as ZigBee. So the mesh network imposes the biggest drain on sensor node battery, but it brings the greatest level of flexibility because each node can connect to multiple other nodes. Depending on the deployment, the mesh network can bring the most reliability and the ability to self-healing to the network, because it can send packet from one point to the other using different paths. So if you look at the point-to-point star and mesh network, the point-to-point seems to be the lowest energy budget, and then the mesh network would require the highest energy budget but the highest reliability and the flexibility. This table summarizes the different characteristics of each of the protocols we commonly use in IoT domain. We can see clear differences between the protocols. For example, ZigBee and sub-gigahertz are typically used for monitoring and control. They also can be powered by coin cell, where the Wi-Fi need to be powered by lithium-ion rechargeable batteries. And if you also look at the number of nodes, so ZigBee and sub-gigahertz can have about 10 to 1000 and 10 to 100, and then the Bluetooth can have less than 10. The Wi-Fi, we are looking at 10 to 250. So the number of nodes have a clear difference across all these categories. Required throughput, usually about 250 kilobits per second for ZigBee and sub-gigahertz. Also same for Bluetooth. Wi-Fi, we are looking at much higher rate, like over 500. The range, the ZigBee and Wi-Fi seems to have similar range, and then the sub-gigahertz can have a very long range, over the 7000, and then the Bluetooth can have about 70 meters. ZigBee is usually the mesh network, but it can configure for star and point-to-point. Both the sub-gigahertz, Wi-Fi and Bluetooth can have both star and point-to-point. ZigBee is focusing on scalability, low power and low cost. Sub-gigahertz, we are looking at long range, but low power and low cost. And then the Bluetooth, again low power and low cost, but it is short range and limited number of devices. And then Wi-Fi, we know that is used for general purpose, for ubiquity in smart home kind of environments, but high throughput. So this table helps you to figure it out what kind of communication protocols you might want to think about for your IoT application. One of the first tasks you need to do when you are designing an IoT system is to select a radio. So if you look at the three options we discussed so far, Bluetooth, low energy, Wi-Fi and cellular, they spend most of the energy when they are communicating and transmitting data, as you can see in the image. And if the radio is on and then not transmitting, still it spent a considerable amount of energy. Only the sleep state is the one that conserve the energy. And as you can see on the other image, when you have a node, the node spend energy in 4 different categories. First, you spend data for data sending, data receiving, collecting data, and controlling actuators. So sending and receiving data is a substantial amount of energy spent on those. Bluetooth low energy radios work well for small low power devices. However, you need to have a gateway to communicate with the internet. Wi-Fi devices require a Wi-Fi network and a router to communicate with the internet. Cellular devices are free from those constraints, especially enabling remote applications and use cases where neither the Wi-Fi or Bluetooth is working. However, compared to Bluetooth and Wi-Fi, cellular consumes the most amount of energy to receive and send messages. Wi-Fi power consumption correlates directly to the amount of data the radio is transmitting. For example, high bandwidth application like streaming music would consume more compared to low bandwidth like transmitting sensor data would consume less energy. So if you are using some kind of video analytics, probably you will need to directly connect it to the AC power or some permanent direct power source. However, we have seen a number of battery powered IoT devices such as security cameras and doorbell cameras being developed where they use some kind of video analytics within them. So it is possible, but it is a trade-off between that you're asking the consumer to change the battery in frequently. To address some of the issues, you can use some kind of triggers. So you will activate the camera only when certain motion detected. So in that way you can avoid data communication or high bandwidth video resolution all the time, or you can process images on the edge and maybe send only the processed and reduce the resolution of data to the cloud. With regards to Wi-Fi, you can put the radio into power saving mode as well, which will use less energy. However, this mode is only used when the radio is not actively transmitting. But it can result in significant power savings and decreased impact to the device's energy budget. Bluetooth Low Energy is one of the most promising low power consumption wireless technologies used in IoT. Most probably you want to keep the BLE device asleep, and when an event occurs, the device will wake up and send the message to a gateway or a PC or a smartphone. So at the end, the active power consumption of BLE is reduced to 1/10 of the energy consumption of a classical Bluetooth. If your application is a low duty cycle application, a button cell battery could provide power up to a year. Therefore, Bluetooth Low Energy is quite suitable for applications that you only need to send a few data packets every now and then. So you don't need to worry about replacing the battery for a year. We have seen this kind of IoT applications in BLE based marketing applications where you put the beacons which runs on a button cell battery for a year in a large shopping mall or a similar location. Cellular 2G, 3G, LTE work very similar to the Wi-Fi power consumption, where the consumption correlates to the data usage. To reduce the cellular power consumption, it is important to choose an efficient, secure communication protocols require minimum overhead. So leveraging dedicated API endpoints to send the data to the cloud could reduce the data usage as well as to conserve the power. For example, instead of programming an IoT devices to send and receive messages directly, what you can do is you can configure them to send data to a cloud service, and then cloud service will store, process, and retransmit the data to anyone who is looking for that data. So for example, if you have a dedicated node to monitor the environment, so you can send a small amount of byte efficient communication protocol to send the data to the cloud, and then cloud take care of sending it to the other subscribers who might be interested in that particular data in your application. This is what is happening in weather stations, where weather stations transmit data to a cloud servers, and the cloud servers such as weather.com cloud, Google Cloud, or NASA will have multiple endpoints and distribute the data to whoever subscribed to those API endpoints. So you can do that the same thing locally in your IoT system if you have any large number of subscribers who are looking for particular IoT device, because otherwise each of these other subscribers will directly send query to that IoT device, which the IoT device need to work hard to fulfill those requests. But here the IoT device directly connect to the cloud once, push the data, and then the cloud will be queried by the other subscribers. So this will help to save the energy from the cellular point of view. When you are designing an IoT system, it is important to minimize the power consumption, the overall power consumption. To do that, you can have an equation where you will calculate what is the power consumption when the radio is waiting, and what is the power consumption when the node is doing something or sending data. And then you can sum them together. But the main critical important factor here is what is the duty cycle. So how often does the node need to send the data to outside? And if you are sending, if the duty cycle is like very large, which means that, for example, 90% of the time it is on, 10% is off, then the entire energy consumption is going to be higher, because the power doing part is much higher than power waiting part. Ideally, you need to design in a way that power waiting is very large portion, and the smaller portion is the power doing. There are three ways that you can reduce the power consumption. The first question you need to ask is, how can we minimize the on-cycle power use? So what you can do is use less time. So you keep the on-cycle least amount of time. Do less, so which means you do less amount of work. Forgo the accuracy, and use a better sensors and microcontrollers that will reduce the energy consumption. Then how do we minimize the off-cycle power? We can wait longer, maximize the off-cycle. For example, if you are sleeping 90% of the time, that is good. And then active sleep, so try to sleep the radio as much as you can. And if you can't do that, maybe put in the standby mode. Use the circuitry to turn device off. And then what is the approach to the design and implementing a system for minimum power requirements? So you need to think about and determine the number of available processors, assess their on and off cycle power consumption. So now looking at not only the radio, but all the entire node as a computation device. Choose the best option for the use case, and then estimate the lifetime. So how long you want to run the entire system, as well as how long you want to run from the one charge or one battery or one cycle. And then apply the minimization techniques that we discussed. Let us now look at how to estimate the power consumption. So given a microprocessor that uses X unit per hour and a battery that has the capacity of Y units hours, and if you assume that microprocessor is used all the time, then you can have this equation where the battery life divided by the processor usage time, and then you can see the number of hours you are going to run the system for. So usually replacing a battery could cost more than the initial cost of the IoT device itself, because if a particular IoT device is deployed in a remote place or where someone needs to physically go and change the battery, that human need to be paid, and that there's a cost for the entire operation. Given that IoT devices are like sometimes 10 pounds or 20 pounds, the replacing battery could cost more than that. So therefore you need to think about how to increase the lifespan of the battery. And also each battery has different qualities, like some are performing differently depending on the load and the temperature and then the environment. So you need to carefully plan what kind of batteries you are going to use. Battery capacity is typically measured in milliampere hours, and when you combine the current and the voltage, you come up with the amount of watt that you need to have in order to power the entire IoT system, node level as well as the entire system. When we are estimating the power consumption, one thing first we need to understand is the voltage. So voltage is defined by the component manufacturer. So we need to provide it. There is no way to provide under or over. So it is something constant. Then for the system to work, we need to meet a minimum current. For example, let's say you have a battery which has 2500 milliampere. So now you want to understand how long that you can run the system. So let's say you have a microprocessor Y, and when it is active mode, including when the peripherals are connected to it, it consumes 25 milliampere. Therefore, in theory, it could last for 100 hours. So this is our starting point. This is the worst case. But we can then consider measuring and transmission requirements that find ways to compress the work into on cycles, then minimize the power usage in the off cycles. Because in this calculation, we assume that the microprocessor is always active. But realistically, you can maybe only need to active for like 10% of the time. And then 90% of the time you are not active. So then you can save a lot. At the same time, what would be the minimum power usage when it is inactive? So if you can reduce that one, that means that you are reducing the 90% of the portion of the time in active mode. You are reducing that entire 90%. This is an interesting table that shows the power consumption of 6 different modules. And for each module, there are different amount of energy consumption based on what each radio does. For example, if the module is sleep, it spends about microamperes. And then when they are transmitting, it is a milliampere range, 30s, 70s, those range. You can see that how much is the difference between sleep and then TX and RX. Because T and RX is in milliampere range, while the sleep is in microampere. It is also important to note that the distance between nodes increases the power used to receive and transmit data. Thus, a saving on a number of gateways could negatively impact on the battery and the ongoing cost. In order to reduce power consumption, we need to write code in such a way that it reduces power consumption. We call this power-aware programming. In the previous slide, we saw that there are different power modes of a processor which can create a major impact on the battery life of the device. In addition to put delays to reduce data volume, we can encode the active inactive period in our programs and send signals to pin to power up, down, standby peripherals, and use bundling work into short bursts within the work cycle. This figure clearly shows the power consumption. For example, if you have seen the blue color, which used for data transmission and communication, is the highest power consumption duration. Data storage is quite little, and if you sleep, it's almost none. And then data acquisition is the one that talk to the sensor and get access to that data. And then the green color denotes the data processing and control. You can see that we have set up the sampling rate to the sensors to update the data every 5 seconds. And then we do the remaining processing and data storage within 1/10 of a millisecond. And we are sending data every 15 seconds. When we think about reducing the power consumption, we can think about shutting down the network interface, but we can also think about shutting down the entire node, and also we can think about shutting down the entire sensor network for a fixed period of time. So in that case, you can wake up all the nodes at a particular time and then do a network communication in a quick burst and then shut down again. In addition to those power conservation mechanisms, we can also think about harvesting energy from the environment using wind, solar, or any other mechanism. But when you are harvesting, we need to think about the power requirements under different loads and different peripherals as well as the network. If you are harvesting energy, for example solar, then the challenge is that there will be a period of time that you don't have the sun. So in that case, you need to have some kind of a battery where during the daytime it gets charged, and then during the night you use the harvested energy. Otherwise, you need to be okay to be not operating the after hours or when the sun is go down at night. So if your application is only need to send the data during the daytime when the sun is there, then that is okay. Otherwise, you need to find a way to power the sensor network or the IoT system during night. A key characteristic of a power-aware programming is that a particular node should be able to change its mood and save the energy by itself. It should not wait for the cloud or any other devices to give any instructions, because that will also increase the network communication as well as the energy consumption. So independently, adaptively change its power mood is an important part of having a long-lasting IoT sensor node. Additionally, in IoT networks, these multiple nodes which compose the system should be able to think as a one unit and be able to collaboratively save the energy across the network, so the entire system has a longer life rather than trying to one individual node trying to increase its lifespan. So this is a collective effort where they exchange the workload and then take turns and then try to collectively save the energy across the system. A power requirement of an IoT device is impacted by 5 different factors: the clock rate of the CPU, the number of processor cores, included peripherals including USB, Bluetooth, Ethernet port, any other peripheral, the processor load, and then the supply voltage level. For example, Raspberry Pi 3, it requires current of 700 to 1200 milliampere at 5 volts. Arduino usually 3.3 volt, 4.74 milliampere. Arduino also has a 5 volt pins, so which you need to provide at 5 volts. If you look at the power consumption, Raspberry Pi 3 requires 3.5 to 6 watt. In comparison, Arduino, both 3.3 volt and 5 volt, consumes about 15 milliwatt and 99 milliwatt. So there's a substantial difference between the two energy consumption in terms of the power. This is understandable because the Raspberry Pi is a fully fledged computer where Arduino is pretty much a microcontroller. Now I would like to revisit a slide which we already discussed in lesson 2, architectures under the fog computing. So if you forgot about that, please go and have a look about that lesson. But in brief, these graphs tell a story where that if you send the data all the time to the cloud to do the processing, it consumes significant amount of energy. Here the last 4, AWS, East, West, EU, Asia, which means that they are sending data all the way to the cloud all the time. And then if you try to process everything on the mobile, which is also consumes more energy. So that is the first one, the mobile only, 3.3 and 16.4 joules. But if you mix the mobile, the fog and the cloud together, where the certain amount of processing happen in the mobile and then certain amount of processing happens in the cloudlet, which is the fog, which is the one hop from the mobile phone, and then the part is from the cloud, then that will yield the least amount of energy consumption. So we discussed at the time that this is the best way to reduce the energy consumption and also to give better performance, because if you are processing complex processing tasks such as augmented reality or face recognition, it might be difficult to do it completely in the mobile phone as well, and even though you do, that will consume more energy here. But if you can use to send the data to a one hop fog node and get the processing there, and then whatever the remaining in the cloud, that will reduces the overall energy consumption. So this is something you need to keep in mind. If you can incorporate any kind of fog computing capability, that is something that you need to think about, and you need to remember that it is good for in terms of the energy consumption, though it might add some other complexities, including some security issues or some higher price, because now you need to add more nodes for the fog. But from the energy point of view, it is a good step forward.